afternoon, students. Good afternoon, Rakshita. Good afternoon, Abhinash. Very good afternoon to both of you. Am I audible and visible? Can you able to see me and hear me? Am I not audible? Can you able to hear my voice now? Am I audible now, Rakshita? What about Abhinash? Can you able to hear my voice? Okay, wait. Am I audible now? Students? Yes. Okay. So I think there is some technical issue from the backend, but no worries. Let us continue with the lesson equilibrium without wasting much time. Okay. So yesterday we have started this equilibrium lesson, right? So let me recall the topics that we have discussed yesterday, and then we will move on to the new topic. Okay. So yesterday we have discussed about the physical equilibrium, and I have discussed about solubility, right? So solubility of the gas decreases if the temperature is increased. And what about the solubility of the gas if pressure is increased? If the pressure is increased, the solubility of the gas also increases. Okay. And also we have studied about Henry's law, which is equal to Kh into the mole fraction, and at equilibrium for a chemical reaction, the rate of forward reaction will be equal to the rate of backward reaction, and for any reaction of this particular type, the equilibrium constant Keq will be equal to the product of the product's concentration divided by the product of the reactant's concentration raised to their stoichiometric coefficient, right? So these are the very important points we have discussed in the yesterday's session. And also from this KEQ formula, we have solved some questions for some reactions, right? So we have taken some 3 to 4 reactions and we have written the KEQ values for this, right? So now there is one more small topic under this chapter. Let us see that and then we will move on to the next major topic, okay? So the last small topic is types of equilibrium. There are two types of equilibrium. One is homogeneous equilibrium and the other one is heterogeneous equilibrium. What is meant by homogeneous equilibria? It means all the reactants and products will be in the same phase. Okay, same phase means if suppose if the reactants and products are in gaseous phase, then it is said to be an example for homogeneous. I will give you an example. So here you see the first reaction, we have nitrogen and hydrogen as the reactant and NH3 is the product. But the phase of all the reactants and products are gases. So it is an example for homogeneous equilibrium. Okay. And for the second reaction, the phase is aqueous. So the phase remains same for the reactant and product, and those are called as homogeneous equilibrium reactions. And heterogeneous means the phase will be different. The reactants and products are in more than one phase. For example, H2O in liquid state is in equilibrium with H2O in gaseous state. So here the reactant and product are in different phases. Okay. And in the second reaction, you see we have calcium hydroxide, which is in solid form, and it is treated with water, which is in liquid form, to produce calcium ion and hydroxide ion. and those ions are in aqueous form. So the phase here in the last reaction, we have more than two phase, right? So we have three phase actually. So it is an example for heterogeneous equilibrium. Okay. So is this clear for all of you? Can you able to understand the homogeneous and heterogeneous equilibrium? It is very easy actually. Nothing to worry much. All right. Yeah. So let us do one question. Let us do one question. Okay. Based on the KEQ concept. So we will do this. What is KEQ for the following equilibrium when the equilibrium concentration of each substances, the value, the concentration values for each substance is given and the reaction is also given. We have to find out the KEQ. So how will you find out what is the KEQ value for this reaction? Can you tell me the KEQ? Can you unmute yourself and tell me the KEQ value for this reaction? Can anyone unmute yourself and give me the KEQ relation for this reaction? This is the reaction. What is the KEQ? SO3 is the product. SO2 and O2 are the reactants, right? So how to write the KEQ for this?
SO2 power 2 into O2 divided by SO3 power 2.
Rakshita, you are making a small mistake in your answer. Can you rectify that and tell me?
SO3 bracket power 2 divided by SO2 bracket power 2 into O2.
Very good. Rakshita, did you find out the mistake that you have made? Yes or no? So first of all, we have to write the product in the numerator, right? So the value should be like this, no? SO3 has to come in the numerator. Then only in the denominator, we will be having the reactants, SO2 and O2. Okay, but anyway, very good guys. So you guys have come up today to give the answer. That's really great. So try to answer like this in the upcoming uh, question for the upcoming questions also. Okay. So I'm very happy that you guys are giving a try for this. Whether you're giving the correct answer or wrong answer, that doesn't matter. Okay, we all are learning, no? So you don't have to worry. You can come up. So don't feel shy that what others will think, what this person will think. Don't worry. Okay? So just give your nobody is going to blame you or nobody is going to think bad of you or wrong of you. Okay? So you don't have to worry. So now what we have to do, this is the KEQ value. But we are asked to find out the value, KEQ value in terms of numbers. So we need to substitute all the numbers given in the question. Okay. So in case of SO3, the concentration is 1.90 molar. So substitute that. So 1.90 the whole square divided by SO2. SO2 is 0.60 the whole square and O2 concentration is 0.82. So we have to substitute like this so that we will get this step. Okay. And on solving this, by doing the multiplication and the division, we will arrive at the answer which is equal to 12.23 liter per mole. Okay. Liter per mole as the answer. Got it. So yesterday we have studied like how to write the KEQ for any type of reaction. But in this question, I am teaching you to apply the values given in the question. That's all. Okay. Nothing big. So any doubt from this? Do you have any doubt from this question? Mahalakshmi and Roshan, we welcome you for today's chemistry class. You have joined little late, it seems. Students, any doubt? Abhinash and Rakshita, shall we move ahead? with the next topic? Yes? Okay. The next topic is properties of equilibrium constant and Le Chatelier's principle. Okay. So under the properties, we will discuss the types first, and then I will discuss the properties and later on applications of equilibrium constant. Then finally, we will discuss about the Le Chatelier's principle. Okay. So let's move into the first topic, which is the types of equilibrium constant. So what is equilibrium constant? KEQ is called as equilibrium constant. Okay. So it has two types. One is in terms of molar concentration, which is represented by Kc, and the other one is called as partial pressure, which is represented with Kp. Okay, Kc and Kp. So both of them, Kc, Kp, both of them are called as equilibrium constant only. But the first one is in terms of concentration. Second one is in terms of pressure. That's all. Okay. For a reaction of this type, Kc can be written like this. Product of the product concentration by reactants concentration, which we have done before. Just now we have done no, in the previous question. The same thing. This capital C in each case denotes the concentration. That's all. But in case of partial pressure for the same reaction, you have to write the pressure value. So in the place of capital C, we will have small c. Oh, sorry, we will have the pressure value, P value. Okay, we will put P here. So Pc power C into Pd power D, the whole divided by Pa power A and Pb power B. Okay, here concentration and there pressure. That's all. So these are the types, two types. Very easy types of equilibrium constant. So now let's go ahead with the relation between Kc and Kp. So this topic is very, very, very important. Okay, for your school exam as well as for your competitive exams. Relation between Kc and Kp. So now I have taken the reaction of type A plus B giving C plus D. Now, if I write the Kp for this reaction, it will be equal to this, right? The partial pressure of C into partial pressure of D by A into D. Okay. So now I am going to do one side calculation for you. Okay. Listen. We know that the ideal gas equation is PV is equal to nRT. How many of you know this relation before? PV is equal to nRT relation. Have you ever seen this formula in any of your previous lessons, in any other subjects in physics or in your 10th class? Yes. Yeah. So PV is equal to nRT is the ideal gas equation. Okay. Okay. Most of you have already are aware of this equation. Yeah. This is ideal gas equation. So where P is the pressure, V is the volume, N is the number of moles, R is the gas constant, and T is the temperature. Okay. Now, if I bring this volume to the other side, what will be my equation? It is P is equal to N divided by V into RT. And N divided by V is called as concentration. Number of moles divided by volume is equal to concentration. So in place of N divided by V, I can substitute C, right? So if I substitute, what will I get? P is equal to C into RT. Okay. C into RT. R is a constant. T is also a constant. Temperature is a constant for this entire reaction. Only thing that will change is the pressure and the concentration for each substance. Suppose if I am writing the pressure for the substance A, what will be my relation? PA is equal to CA into RT, right? For PB, PC and PD, we will be writing accordingly. CBRT, CCRT and CDRT. Okay, clear? Now, in place of PA, PB, PC and PD in this relation, okay, if we substitute all these values, what we will get? Put all the values, 4 values in the above equation. If you put, you will get the relation like this, right? So in place of this PC, I will have CCRT to the power C. The same way for other substance also. If you substitute, you will get a relation like this. Now, something is common for all the 4 substance, right? What it is? Something is common, no? What it is? Which term is common for all the 4? Very good, Rakshita. It is RT. Yeah. Yes, Roshan. It is RT. So we can take RT outside. Okay. But RT also has some power. Here it has C, here D, and here A, and here B. And take all the concentration out first. Okay. And if you take the common term RT outside by keeping the powers like this, since C and D are in the numerator, it is written like this, and A and B are in the denominator, no? So A plus B, if it goes to the numerator, it becomes minus A plus B. So that's why I have written the minus here. Got it? Now, what is this? What is this? What is this? Can anyone tell me what does this term denotes? Can anyone find out what does those 4 terms denotes for the reaction, for this reaction? Very good, Rakshita. It is molar concentration, equilibrium constant in terms of molar concentration, right? So instead of that 4 substance concentration terms, I can write Kc. Okay, this is nothing but Kc, equilibrium constant in terms of molar concentration. And this term is written as delta Ng. Delta Ng means change in the number of moles of gaseous. Delta Ng means number of moles of gaseous product minus number of moles of gaseous reactant. So this is the number of moles of gaseous product, right? C plus D. C plus D are the number of moles of gaseous product, and A plus B, they are the number of moles of gaseous reactant. So instead of writing this entire thing, I can put delta Ng. Okay. So the relation between Kp and the Kc, the relationship between Kp and Kc is this. Kp is equal to Kc into RT power delta Ng. Okay. To RT power delta Ng. So this is the very important relation you should write down in your notebook. Okay, so this relation will be very helpful for you to solve many simple and easy questions. Okay, so don't get confused. Please memorize and by heart the relation as it is. Kp is equal to Kc into RT power delta Ng. So some students, what they will do, they will memorize in the other way around. They will put Kc in the left hand side. Kc is equal to Kp into RT. So please don't do those things, okay? That's what I told you, no? How delta Ng came. Mahalakshmi. So it is the number of moles. Small a, small b, small c and small d are the number of moles. Okay. So this is the number of mole of product and this is the number of moles of the reactant. Number of moles of the gaseous product minus number of moles of the gaseous reactant. So this is actually equal to the change in number of moles of the gaseous substance. Got it? Suppose if I want to write delta H, what I will do? I will do final enthalpy minus initial enthalpy, right? So in the same way, it is written as delta Ng. Can you able to understand? Mahalakshmi, do you have doubt in this? Yes. So now we will go for one question. So all of you are going to give a try over here. So I have three reactions for you. You have to give me the expression showing the relationship between Kp and Kc. So can you guys try for it? So I will do for the first reaction and for the remaining two you try to do. Okay. So let us take the first reaction. N2 plus 3H2 giving 2NH3. So first of all, to write the Kp-Kc relationship, I need to find out the delta Ng value, right? Delta Ng value, which is the summation of number of moles of product plus summation of number of moles of reactant. So the number of moles of product is 2 and the number of moles of reactant is 3 plus 1. So it will be 4. 2 minus 4. Sorry, here you should have minus, okay? It is not plus, it is minus. So 2 minus 4, so the answer is coming out to be minus 2. So we have to substitute this minus 2 in the formula. So what we will get? Kp is equal to Kc into RT power minus 2. That's all. So this is the expression for this reaction. Okay. So can you guys try for the second reaction? Who wants to try for this? One of you have to unmute yourself and you have to tell me the answer. So before giving me the Kp-Kc relationship, tell me the value for delta Ng for this reaction. What is the value of delta Ng here? Find out fast.
1.
Very good. It is 1. Who said? Okay. So delta Ng is equal to 1 because we have two product with 1 mole each. So 2 minus 1 is 1. What is the relationship between Kp and Kc? Kp is equal to Kc into RT power 1.
Kc into
That's all.
RT.
Yeah, very good. So try for the third one. Try for the third reaction. Yeah, very good, Roshan. What is the answer for the third reaction? What is the value of
Kc.
delta Ng? What is the value for delta Ng?
Zero.
0.
Very good. 0. Delta Ng is 0. So the relation will be
Kp equal to Kc.
very good. Kp is equal to Kc because RT power 0 we will have. So anything to the power 0 is equal to 1, right? Anything to the power 0 is equal to 1. So RT power 0 becomes 1. So Kp is equal to Kc for this reaction. Okay, very good. So now let us go for one more question. Okay, in which some numericals, numbers will be there. So we will try to do that from the same concept. So here is a question. At 450 Kelvin, Kp is equal to 2 into 10 to the power 10 per bar for the given reaction at equilibrium. What is the Kc at this temperature? Kp is given, okay, Kp is given, temperature is also given, reaction is also given, and from this reaction we can find out the delta Ng, and they are asking us to find out the Kc. So what we have to do? We have to take the Kp-Kc relationship, right? This is the reaction and we have to take Kp is equal to Kc into RT power delta Ng. R is a constant. T is given in the question. Kp is also given in the question. We are asked to find out Kc and we can able to find out delta Ng from the given reaction. So ultimately the first step that we have to do is finding out the value for delta Ng. Okay, delta Ng will be equal to 2 minus 3. 2 plus 1 is 3. So delta Ng value is minus 1. Okay, so substitute. Take the relation with the desired relation and substitute. So you can also rearrange the equation like this. because we are asked to find out the Kc, right? So keep Kc one side, and on the other side we will have Kp divided by RT, okay, power delta Ng, and that delta Ng is equal to -1. So this is in the denominator with the power -1. So if it goes to the numerator, we will have Kp into RT power +1, which is equal to Kc. And that is what we have got. Okay. So Kc is equal to Kp into RT. Now, what is the value of R? What is the value of R? Can anyone tell me the value of R for this reaction? The Kp is given in terms of bar, right? So in terms of bar pressure, it will not be 8.314, my dear Roshan and Mahalakshmi. It will be 0.0831. Okay, your answer is correct. So that is also 8.314 is also the value of R, but that we have to use if the pressure is given in terms of liter atmosphere. Okay, or in terms of joules. If you are representing your answer, then you can use that for it. Okay, but here we are having the pressure value in terms of bar. So it will be 0.0831 liter bar per Kelvin per mole. Okay, is it clear for all of you? So please take down the universal gas constant value for both joule per mole and bar liter per Kelvin per mole. Clear for both of you? Roshan and Mahalakshmi, did you get it?
Yes, ma'am.
So while substituting the value of R, you need to check the unit, okay, given in the question. Accordingly, you have to do. Otherwise, you will end up with the wrong answer. Okay, for physical chemistry, unit is very, very important. So before doing any numericals, we need to be very careful with the units first of all. Okay, so unit conversion is very important for solving the numericals. So just have your eye on it before going for the calculation. Okay, now you can substitute the value. So substitute the Kp value, R value, and the T value. So just the simple multiplication. 2 into 10 power 10 into gas constant into temperature. If you multiply this entire thing, you will get the answer as 7.479 into 10 to the power 11 liter per mole. Okay. Can you all able to understand? Can you all able to understand? Shall we go ahead with the next topic? Yes? Okay. So we have discussed the types of chemical equilibrium, and from that we have studied on relation between Kp and Kc. Now we will go into the properties of equilibrium constant. Okay. So the next topic is properties. The very first property of this Keq, okay, which is the equilibrium constant, is it is reaction specific. Okay, it is specific for a particular reaction. It is not a constant value for all the reaction. So each reaction has some specific equilibrium constant value. Okay, so it is not like a gas constant. Gas constant is a universal constant. Okay, for any type of reaction, we will substitute 8.314 and 0.08 and all. But equilibrium constant is not like that. It is specific, unique for a particular reaction. Okay. And the second property is for a given reaction, Keq depends only on temperature. Okay. Keq dependency is only on temperature. It is directly proportional to temperature. Okay. And the third relation is very important. Third property is very important. Listen carefully. I have taken A plus B giving C plus D reaction. So what will be the equilibrium constant for this? It will be C into D divided by A into B concentration, right? If I reverse this equation, if this equation is reversed, how does it look like? It will be C plus D, which is in equilibrium with A plus B, right? I have reversed this equation and I have got this. Now the new equilibrium constant will be, let me take the new equilibrium constant as K dash. So for K dash, the products are A and B and the reactants are C and D. So the relation will be A into B divided by C into D. Okay. So if the equation is reversed, I am getting a new equilibrium constant. Now the relationship between the first old equilibrium constant and the new equilibrium constant will be K dash is equal to 1 by K. K dash is equal to 1 by K. Please write down this in your notebook. If the equation is reversed, then the new equilibrium constant will be the reciprocal of the old equilibrium constant. Okay. All these relations will be very helpful for you while solving the numericals. Okay. I will give you some questions. In that you can understand that how this concept is being applied over there in the question. Okay. In the question, they will give the one value for K. Okay. And they will ask some other, they will give some other equation and they will ask us to find out the equilibrium constant for the equation which they have given. Okay. So in that case, we have to look into the reactants and products. If it is getting reversed, then we have to take the inverse of it. It is very easy only. So if I practice some questions based on this topic, you will get to know. So don't worry. So did you all understand this point? Do you have any doubt? Very easy, very simple. If you are reversing, just take the reciprocal. That's all. Shall I go for the fourth property? Third, fourth, and fifth. Okay, so these three properties are very important. Do you understand the third property, students? Shall we go for the next? Okay. Yeah, I'll go for the fourth property. The fourth property is take the same reaction and for this reaction, K will be written like this. Okay, this is not going to change. Now, what I'm going to do, I'm going to multiply this equation by a number n. Okay, I'm going to multiply this equation by a number n. It can be, the n can be 2, it can be 3, it can be anything. I can multiply by any number. If I'm going to multiply any such equation by any number, I will get a new equation like this, right? Na plus Nb, which is giving Nc plus Nd. So the n is the stoichiometric coefficient. Okay. So while writing the equilibrium constant, we have to write the stoichiometric coefficient in the superscript, right? So the new equilibrium constant K dash will be equal to C power n D power n divided by A power n B power n. Okay. Since n is common for all, we can write like this. This is the new equilibrium constant. Now, what is the relation between the old and the new? In the old, we don't have any number, but in the new equilibrium constant, we have a number. So, K dash will be equal to K power n. K dash will be equal to K power n, right? So, this term is nothing but the K. This term is nothing but K. So, we have the power. So, K dash is equal to K power n. All right. Can you all able to understand the simple relation? If I am reversing the equation, I have to take the reciprocal. If I am multiplying the equation by some number, and that has to go to the power. That's all. K dash is equal to K to the power n. Okay. Shall I go for the fifth property? Do you have any doubts from this? Do you have any doubts from this? No. So let's go for property number 5. So here I am going to break down my equation into two. So first, let me take A giving C and the next one is B giving D. Okay. So what will be the equilibrium constant for the first reaction? K1 will be equal to, the product is C and the reactant is A. So K equilibrium constant is equal to the concentration of C divided by concentration of A. This is taken as equation 1. What about for the second reaction? K2 is equal to concentration of D divided by concentration of B. And this is equation number 2. Now, if I add these two equations, what will I get? In the reactant side, I have A and B. In the product side, I have C and D. So while adding, I will get A plus B, which is in equilibrium with C plus D, right? Now, what will be the equilibrium constant for this? K dash is equal to CD by AB. Okay. So C by A, the C by A is equal to K1 and the D by B is equal to K2. So K dash is equal to K1 into K2. If I'm adding two equations, then I have to multiply the equilibrium constant of those two equations to get the new equilibrium constant value. Is it clear for all of you? Do you have any doubts here? So what was the first thing? If I'm reversing an equation, then I have to take the reciprocal, right? If I am multiplying the equation by some number, then I have to take that number to the power. If I am adding two equation, then I have to take the multiplication of the two equilibrium constant value. Is it clear for all of you? Any doubt? So these are the very important 5 properties of this equilibrium constant. Clear? So please keep these last 3 points in your mind. Don't forget, don't get confused. Please be thorough with it. All right? Shall I go for the next topic? Shall we go for the applications of equilibrium constant, students? Properties and the types part is clear to all of you, right? Yes. So now let's go for the applications of equilibrium constant. So what is the use? What is the first application? First of all, we can predict the extent of the reaction from the KEQ value. Okay, we can find out that how long the reaction has went and what is the extent of the reaction from the equilibrium constant value. Okay, I'm having a reactant and the product. If the equilibrium constant is greater than 10 power 3, okay, then the KEQ will be P by R, right? So if it is greater than 10 power 3, it means that the numerator, that is the concentration of P is in large amount and the denominator, which is the concentration of R is in very small amount, negligible amount. Okay. So in that case, since the numerator is very big, we can say that the reaction proceeds almost to completion. So the extent of the reaction is, it is going to get completed. Okay. If the KEQ value is less than 10 power 3, if it is less than 10 power 3, then it shows that the product concentration is negligible and the reactant's constant denominator is more. Okay. And this denotes reaction hardly proceeds. I mean, only very few amount of the reactant has been converted to the product. Okay, so that is the meaning. And the third case is if the KEQ value is between these two numbers. If it is greater than 10 power 3 and if it is less than 10 power 3, then it shows that both reactant and product are in equilibrium. Okay, because in one case it is less and in the other case it is more. In this case it is less and in this case it is more. So we can say that they are in equilibrium with each other. Got it? So neither the numerator nor the denominator is in excess amount. So it is in equilibrium. Got it? So this is how you can find out the extent of the reaction. Got it? So now we will try to solve one question from this concept. Are you all ready? Shall I go ahead with the question? You want to note down anything from the slide? Students? Shall I go for the question? Yes? Okay. Here is the question. In which of the following cases the reaction goes fastest to completion? K value is given for 4 cases. Tell me for which case the reaction goes fastest to completion. In case of 4, Abhinash, fourth option.
Yes, ma'am.
Very good. That is exactly the correct answer. Because the equilibrium constant is greater than KEQ value is greater than 10 power 3, right? Very good, Roshan Mahalakshmi. Answer is correct. Higher the value of K, faster is the rate of the forward reaction. So option 4 is the correct answer. Option 4 is the correct answer. Okay. So now the second application is we can predict the direction of reaction from equilibrium constant. So you see here, R is giving P and we are writing the reaction quotient and it is equal to P by R, concentration of P by R. So actually we write P by R and we put it is equal to KEQ, right? But here instead of K, Q is written. So when we have to use K and when we have to use Q, Q is written at any instant of time, whereas K is written only at equilibrium. Okay, only at equilibrium. So as we know, every system tries to attain equilibrium. So Q is equal to K. We know that all the system will attain the equilibrium state. So instead of writing Q, we can write K, but both of them are equal. Okay, both of them are equal only. At equilibrium point, Q is becoming equal to K. So you can predict the direction of reaction using the Q value. I will tell you how to predict that. Okay, let me show that to you in the next slide. So here you see the Q versus K. Q versus K graph. So we have 3 cases here also. In the first case, K is greater than Q. In the first case, K is greater than Q, and in the second case, both of them are equal. In the third case, Q is greater than K. Okay. So if K is greater than Q, or if it is trying to go to be equal to each other, then we can say that the reaction is moving to the forward direction. Reaction is moving to the forward direction. So the highest K value is becoming equal to the Q value. Okay, if it is so, then we can say that the reaction is proceeding towards forward direction. If the Q is coming equal to K, here you see in the third case, Q is greater than K. So if the Q is trying to get equalized with K, then we can say that the reaction is proceeding towards backward direction. Okay, it is proceeding towards backward direction. Got it? This is how you can find out the direction of the reaction using the K value and the Q value. All right. So now moving ahead with the third application, we can calculate the standard Gibbs free energy for this reaction, for any type of reaction from KEQ value. So we have already studied the relationship, right? So if our reactant is in equilibrium with the product, the delta G value will be equal to minus 2.303 into RT into log of KEQ. So we have already studied this relation in thermodynamics lesson. Okay. Standard Gibbs free energy can be calculated using equilibrium constant. So how to calculate? If the KEQ is greater than 1, then it means delta G will be less than 0. Right? If it is greater than 1, we have a minus symbol here, no? So the negative of any positive will be less than 0, will be negative. So delta G will be less than 0. So if it is less than 0, if it is less than 0, it means it is negative. Delta G naught is negative. So I told you, right? All spontaneous process will have the negative delta G naught value. If the delta G is negative, then it means the process is spontaneous. In the last lesson itself, I taught you this. And we can say the reaction will proceed towards forward direction. Okay. And if the KEQ value is less than 1, obviously minus into minus will become plus and delta G will be positive. If the delta G is positive, then the reaction is non-spontaneous. And if the reaction is non-spontaneous, it will be going towards backward direction. Okay. And if KEQ value is equal to 1, if it is equal to 1, delta G will be equal to 0. If it is equal to 1, it will be equal to 0 because here we will substitute 1, right? And log 1 value will be equal to 0. So 0 into anything will be 0. So delta G will be 0. Okay. If it is 0, then the reaction is in equilibrium with each other and there is no shift in any direction. The reaction will not shift towards forward direction or backward direction. It is in equilibrium. All right. Can you able to understand? Any doubt from this? Do you have any doubt here? So what are the 3 applications, students? First of all, we can find out the extent of the reaction. And secondly, we can find out the direction of the reaction. Thirdly, we can calculate the delta G naught from the equilibrium constant level. All right. Shall we go ahead with one question? Are you ready? Since you guys have joined late today, I would like to take some more minutes. Don't worry, I will just take 2 or 3 more minutes and then I will close the class. This is okay for all, right? Shall I take? Yeah. So without wasting the time, I'll go ahead with the question. So this is the question. Question looks bigger, but don't get scared of seeing the question. It is easy only. So listen. Equilibrium constant is given for this reaction. Equilibrium constant Kc value is given for this N2 plus 3H2 giving 2NH3 reaction. It is equal to 0.061. This is the Kc value. And the temperature is given as 500 Kelvin. At a particular time, the analysis shows that composition of the reaction mixture is 3 mole per liter nitrogen, 2 mole per liter hydrogen, and 0.5 mole per liter ammonia, NH3. Now we have to find out whether the reaction is at equilibrium. If it is not in equilibrium, we have to find out in which direction it goes to proceed to reach the equilibrium. Okay. So first let me write the given values. Let me write the concentration of all the 3 species and the KEQ value which is given in the question. So now what we have to do, we have to find out the Q because we do not know whether it is in equilibrium or not, right? Only if it is in equilibrium, we can write K. If it is not in equilibrium, we have to write Q. Okay. But the expression is same only. Q is also equal to the product concentration raised to the power stoichiometric coefficient divided by the reactants concentration raised to their stoichiometric coefficient. Expression is same. Now you substitute all the values in this expression. So what is the concentration of NH3? It is 0.5. And accordingly for N2 and H2 also you substitute. If we substitute, we will get the answer as 0.0104. So can you guys find out whether the reaction is at equilibrium or not? We have 2 questions. Tell me the answer for first question. When will the reaction be at equilibrium? Only if K is equal to Q, right? Only at this condition, we can say that the reaction is in equilibrium. Now, this is the value of KEQ and this is the value of Q. They are not equal. They are not equal. It means they are not in equilibrium with each other. Reaction is not in equilibrium. Answer is no. If not, in which direction it will go? Will it proceed towards the forward direction or backward direction? What is your answer? How will you find out whether it is moving towards forward or backward? How will you find out that? Again, by comparing the values only, no? Just compare and tell me. Tell me whether Q is less than K or Q is greater than K. If Q is less than K, then it is clear that the reaction is proceeding towards forward direction. If Q is greater than K, it means that the reaction is proceeding towards backward direction. I have given you the hint for finding out the answer, right? What is the answer? Will it move towards forward or backward? Yeah, forward. Because the K value is greater. It is 0.06. But here 0.01. So K value is greater than Q. So the reaction will proceed towards forward direction. Okay? Can you all able to understand how to apply the concepts we are learning? Yes? Or still you are in the confusion? So by solving questions like this, you will get to know how to apply the formula and how to apply the theory which we are learning. Okay, so you don't have to worry. So here we wrap up today's session. Okay, so tomorrow we will study the Lee-Chatela's principle. Okay, thank you so much for attending. Please give your feedback over here and then you can leave the class. Okay, thank you so much for all of you. Thank you so much, students. I have launched a poll. Please give your feedback over here and then leave the class. Thank you, Abhinash. Thank you so much, my dear.